Imagine you're in the middle of your exam, a stressed mathematics student. You stare into your paper, confused. You see an integral. You're scared. Sweat starts rolling down the sides of your face. The stress is getting to you, and you can't think straight. Time is running out, and while you're stressing, a sudden realization comes to you. What if you just wrote the integral differently, in a way that's easier to solve? You see, there's a lot of problems that are just like this when it comes to integration, where in its original form, an integral can be extremely difficult to solve. So what's the solution? I'm glad you asked. Now here's the thing. These integral transforms are essentially a technique that allows you to take an integral and map an equation from its original domain to another domain. The solution can then be reversed back to the original domain by using the inverse of the integral transform. Usually transforms are done in the following form. We have our transform t, the input function f, and the output being a function tf. An integral transform is a specific type of mathematical operator. There are a lot of useful transforms, each specified by the choice of the function k with two variables known as the kernel. Some have an associated inverse kernel, which would give us the inverse transform. So what are some real-world examples of this? There's the Fourier transform, Laplace transform, Laguerre transform, Legendre transform, Hilbert transform, and finally, the star guest of today's video, the Mellin transform. Each transform has an associated table of commonly used transforms, and here are some examples. But let's dive more into the Mellin transform. Going back to our struggling math student, let's take a look at that integral of theirs. Now at first, this might seem incredibly difficult. The key to this integral is to do some splitting and use our analysis skills, as well as applying our one and only Mellin transform. We see the integral is bounded and that there are two parts. So let's split it, since that seems like the most reasonable option so far. And now we read the left side first. With some rearranging, we can write this integral in this form. Then we rewrite the right side as this. Now let's let some arbitrary answer, I of s, equal the two integrals combined as one in the following form, where s is a complex number. Note that we were able to get to this form by applying a Mellin transform. We see that the left side is just equal to the equation of the gamma function for variable s, but the right side is not quite so easy. First of all, the integral typically diverges, but we're not going to let that scare us away. Within our strip of convergence from 0 to 1 for the real component of s, we recognize this as a beta function. Given this definition of the beta function, we can use its known relation to the gamma function as shown. We see that the left integral maps directly to just the gamma function with z1 and z2 added together, given the gamma function definition, but the right side would be the beta function. So by rearranging, the beta function satisfies this equation here. Next, we need to solve that typically divergent integral by parameterizing it and defining a strip of convergence for our complex variable s. In order for the integral to not diverge, the real component of s must be less than 1 and greater than 0, and this is because of how we define our parameterization in terms of t as shown. As our parameter t approaches 0, we need the gamma function to converge. Near 0, the x to the power of s minus 1 term would converge when the real component of s minus 1 is greater than negative 1, aka the real component of s is greater than 0. Additionally, as t approaches infinity on the other hand, by only considering dominating terms, our gamma function behaves as the following integral with a x to the power of s minus 2 term instead. In order for this integral to converge in not just this case but the previous one as well, the real component of s minus 2 must be less than negative 1, aka the real component of s must be less than 1. So to meet both constraints for our parameterization to work, we say 0 is less than the real component of s, which is less than 1. Back to the integral, we do our substitution, do some rearranging and cancelling, and we get an integral that looks a little strange. It looks like the beta function. z1 would be s, and z2 minus 1 equals negative s, therefore we have a beta function in terms of the real component of s and 1 minus the real component of s. Plugging this into our gamma function and beta function relation, we get gamma of s minus gamma of 1 minus s, all divided by gamma of 1. And then if we simplify and use the Euler reflection formula, our answer for the right integral would be pi times the cosecant of pi s, such that s is a complex number that is not a member of z, meaning valid for any non-integer complex number. You're welcome, stressed out student. So combining our answers, I of s equals gamma of s minus pi cosecant pi s for 0 is less than the real component of s less than 1. But I forgot to mention something. In order to define our left integral, we also need to define a strip of convergence there as well. In this case, the real component of s must be greater than 0, meaning the common domain between the two integrals is 0 is less than the real component of s, which is less than 1. And we got the real component of s is greater than 0 for our integral from doing some graphical analysis, which I'll explain now. So given this graph of the gamma function, we see that as we approach x equals 0 from the right side, we hit a vertical asymptote. Considering the function's definition, the main dominant term as we approach x equals 0 is the x to the power of s minus 1, so in order to have convergence, the real component of s minus 1 is greater than negative 1, so the real component of s is greater than 0, as otherwise our function would diverge. As x approaches infinity, we have an exponential decay towards 0, meaning that we still have convergence. Thus, our integral definition for our gamma function converges for the real component of s is greater than 0. Okay, now we understand that, but we have another issue. What if I told you that despite all of what I just said, if I were to say the real component of s equals negative 1/2, for example, and just plug it into I of s, we actually still get a converging answer, which would be, in this case, negative square root of pi plus pi. If we plug it in the individual integrals, we still see they both diverge individually. So before you start losing your marbles, there is actual mathematical reasoning behind why we can just do that and get a converging answer outside of our region of convergence for each part of our integral. And it's just that, they're parts. I of s itself can converge despite one of the parts not being convergent due to the process of analytic continuation. Analytic continuation is this method of extending the domain over which a complex function is defined, extending the function to be analytic on a bigger region. The full definition of analytic continuation is as follows. Suppose we had some f of z function which is analytic on a region A. Now let's say a region A is contained within another region B. We say that f can be analytically continued from A to B if there's a function f hat of z such that 1, f hat of z is analytic on B, and 2, f hat of z equals f of z for all z in A. But what really makes this Mellin transform so special? Well, it's used in a variety of fields including number theory, statistics, the theory of asymptotic expansions, etc. It also has close ties to the Dirichlet series, which is any series of this form such that A sub n is a complex sequence and S is a complex variable, and is a special case of the general Dirichlet series, where lambda sub n is a strictly increasing sequence of non-negative real numbers approaching infinity. The most famous example of a Dirichlet series is actually the Riemann zeta function, defined by the following. But that's going a little too far ahead. For now, just know this transform has some very interesting ties into other aspects of mathematics, but we can talk about those some other time. As for the Mellin transform itself, a proper introduction to it is how it's a transform of a complex function defined on the multiplicative group r equals 0 to infinity, defined by the following integral. Here's an alternative form of this integral. However, do note that dx over x is a Haar measure on the multiplicative group. What that means is we get a translation invariant integral. Say we had a straight line. On this line, ordinary length is translation invariant. That basically means that a segment that is 5 units long will always be 5 units long, whether it's at position 0, 100, 200, etc. The Haar measure generalizes this property of keeping the same measure to more abstract groups, like in our Mellin transform. But why is dx over x a Haar measure? Say we just use dx. Under multiplication, it wouldn't be invariant, because if we had, say, the interval from 1 to 2, we'd have length 1. And if we multiplied that interval by 10, go from 10 to 20. But now we've changed the size of the length to 10. It's no longer 1 anymore. But if we use dx over x, say we used this integral from 1 to 2 versus an integral from 10 to 20, in both cases our final answer is still the exact same, ln of 2. Back to the Mellin transform, here would be the inverse of it. This notation implies that this is actually a line integral taken over a vertical line in the complex plane with a real component c that has to be within the strip of convergence of the Mellin transform. This equation is also provable using the Fourier inversion theorem and is very useful for some high-level integrals. But you might be asking, what's the easiest way to evaluate most Mellin transforms? Some can be evaluated directly from the definition, but others require the application of Ramanujan's master theorem, which is defined as shown. It requires, roughly speaking, that phi of negative x is a quote-unquote well-behaved sort of function, having both no poles and no factorial-like growth in the left half plane, or as the imaginary component of s approaches infinity. For example, if we had the integral of sine of x to the n dx from 0 to infinity, we first determine that the integrand will converge when n is greater than 1, which is proven by the Dirichlet test for improper integrals, which I'll explain after we get our answer. Moving on, we rewrite the integral in a more useful form. So for n is greater than 1, we parameterize x to the n equals t, meaning x equals t to the 1 over n, and dx equals 1 over n times t to the power of 1 over n minus 1 dt. So we have our integral in the form of 1 over n times the integral from 0 to infinity of 2 to the 1 over n minus 1 times sine of t dt. Then we write out the expansion of sine of t, and that allows us to realize that phi of n equals sine of negative pi over 2 times n by analyzing how the signs oscillate in our expansion. By plugging this into our formula, we get that the integral equals 1 over n times gamma of 1 over n times sine of pi over 2 times n. For the special case of the Fresnel integral, sine of x squared, meaning n equals 2, we get the answer square root of pi over 8. Back to the Dirichlet test for improper integrals. All it really says is given two functions, f and g, such that they map a to infinity to the real domain, they must follow the two following conditions in order for the integral from a to infinity of f of t times g of t to converge. The first is that f must be monotonically decreasing, meaning f is decreasing, and f of t approaches 0 as t approaches infinity, and 2, g is continuous, and there exists an m such that the absolute value of the integral from a to x of g of t dt is less than or equal to some m for all x is greater than a. For our case, if we let f of t equal t to the power of 1 over n minus 1 for some n greater than 1, this function decreases monotonically to 0. This means that g of t would equal sine of t, which we know is continuous by the fact that sine is continuous by definition, and we prove it is bounded in that the integral from 0 to some arbitrary x of sine of t with an absolute value around it would be equal to the absolute value of 1 minus cosine of x. We know that cosine of x oscillates between negative 1 and 1 as x approaches infinity, meaning that the integral of g of t from 0 to x oscillates between 0 and 2. It's bounded by m equals 2 for all x greater than a. So our original example integral does indeed converge for n greater than 1. If n were not greater than 1, the test would fail and we don't get a converging answer. But there's more to the Mellin transform though. It can be defined in terms of the two-sided Laplace transform shown here. It also has a very powerful scale invariance property, meaning that the magnitude of the transformed and scaled function is identical to the magnitude of the original, making it a good tool for use in the analysis of algorithms. Another crazy thing about this transform is its connection with the famous Riemann zeta function. We're going to let f of x equal 1 over e to the x minus 1 and let the real component of s be greater than 1. Applying the Mellin transform to f, we get an integral of the following form. We can then rewrite 1 over e to the x minus 1, that specific term, as a series from n equals 1 to infinity of e to the negative nx using the geometric series formula with some rearranging. Taking the sum to the outside of the integral, we then parameterize nx equals t such that dt equals n dx. Rewriting, we get the following expression. We then simplify, and we get this. If you didn't know, the left side is actually the Riemann zeta function, and the right side is the gamma function. So our final answer is zeta of s times gamma of s for the real component of s greater than 1. Now there are even more insane things you can do with the Mellin transform, but I think they're a little out of scope for this video. So thank you for watching, and I hope you learned something. Until next time.